joining and for your interest in this section. It's always very hard to, choose the section, but I hope together with Crystal and Drew, we're going to give you a few insights on the BESS sector, which has been quite active for the past year, and also the year to come. It will be more and more active. Okay. What we want to talk about today is what happened in the last few years. What are the main drivers that are behind the boom in the BESS sector? As well, most of us are also engineers and scientists, so we want to shed a light on what's happening on the technological level, and also, like as many sectors that are increasing a lot, there are always some bottlenecks and problems, and so we want to also go deeper in details about what prevent the BESS sector to scale up even more rapidly than it's doing right now. Let's start with the market shape and economics. A few details about how the battery sector changes in the last 5 years. As you can see, both in gigawatt and gigawatt hour, this is a booming sector. Every year there is 40% increase with respect to last year. This past year was quite eventful because for the first time, the global installation passed that limit of 100 gigawatt, which is 30% more, 40% more than last year. As many sectors in the battery value chain, this sector is also dominated by China, which accounted for more than 50% of the installation. But we're also seeing a huge development, for instance, in the Middle East. Another trend that we can see is the differentiation between the application or the sector of the BESS, because from the outside perspective, all the BESS looks equal, but there are different applications, different size. The one that is most discussed is the one that is connected to the grid, the utility scale level. Usually these applications are in the tens and hundreds of megawatt or even gigawatt at this point. But then there are also other sectors like the residential, so batteries that are typically in home, or commercial and industrial, so more or less below 5 megawatt. And in these two graphs, we can see that there is a huge trend, which is the shares of residential and C&I is decreasing, and in 2025 was single digit for the both of them, which gives a sense of how the industry is evolving, because before this technology wasn't, especially lithium ion, were not considered suitable or technologically advanced enough to be able to sustain big projects. But actually in the last couple of years, we see an exponential of development of these big projects, which means that this technology is more mature, and both developers and investors are more confident that this project can arrive to termination and also guarantee the gigawatt and the energy that they guarantee on the paper. So as we see, utility scale dominated more than 80% of the project in 2025 were utility scale. Talking about regions, as I said before, China is still the dominating factor within the installation. United States, despite the policy and that sometimes is contrarian to the development of renewable energy and energy storage, is still maintained a second solid place. And then we see the huge expansion of Australia and Saudi Arabia, which are expanding markets that are mainly driven by big utility scale projects. While Europe, we still have Italy, Germany, and United Kingdom as the main market. I mean, even if in the chart you see some countries that went up, some countries that went down, it must be noted that all these countries, like their development in 2025 was higher than 2024. So they all grew, but some of them grew faster than the other one. Being behind this chart, I can tell you that maybe the only one that didn't grow in the last year was North Korea and Japan. But as regard of the other one, all of them had more development in 2025 than 2024. And then I pass the word to Drew. Please tell me when you want to change the slide. I will do that for you.
Great. Well, thank you so much, Alex. So as Alex walked us through, there's been a huge explosion in, I shouldn't say explosion. There's been a massive increase in the number of battery projects deployed. And there's a few big drivers of that. And I think by far one of the biggest drivers is the declining costs of energy storage. So that starts at the cell level and then cascades down to the various other parts of the BESS, the module, the enclosure, as well as some of the other key components, such as the PCS or the inverter. Or PCS is another name for the inverter, MVT, which is the medium voltage transformer, and the EMS. So it's become common now in the industry for most suppliers to supply all these things together, the DC block, the PCS, the medium voltage transformer, and the EMS. It doesn't always happen that way, but I would say more than half of projects have a single supplier. In some cases, it's a single product, as we'll see later in the presentation. But whether it's a single product or multiple products, those are what we would call the key components. So if we look at those key components, and this data here comes from Bloomberg New Energy Finance, you can see there's continued to be dropping prices. There was a bit of an anomaly in 2022 where prices went back up, but overall they've continued to drop. And from 2024 to 2025, we had a 31% drop year over year in energy storage costs for that key equipment. To be clear, there's still a number of other costs that any project needs to purchase for a fully functioning BESS. For example, the cost for interconnection, for development, for high voltage transformers, all the other things. But generally, those are less than half of project costs. Most of the costs are in this key equipment, and that continues to go down. One important thing to note is that there's a lot of variability across different markets. And if you look on the right, you can look at those key equipment costs. If we look at costs in China relative to costs in the EU, it's almost double. So where you are has a huge impact on how much you're going to pay for one of these systems. I'm based in the US. I think the US pricing is pretty close, if not more than the EU pricing. And then there's other places in between. On the right, we see Saudi Arabia, which is as Alex mentioned, an area where there's a lot of growth. The second chart points out that when you get really big systems, the costs come down quite a bit. So you can see even in the EU, you have much lower costs for really big systems, whereas a lot of other components in other markets stay at similar costs. Next slide, please. Another really important trend that we've seen changing over time is the duration of energy storage. Duration is a ratio of the maximum energy that can be output the system divided by the maximum power. In other words, if the battery is fully charged and it discharges at its full rated power, how long can it do that discharge? LFP, which is the technology we see in most utility scale projects, is really its sweet spot is anywhere from 2 to 4 hours. And you can see that that aligns with the average duration of all projects around the world. Utility scale, you can see a split out here of like the overall versus only utility scale durations, and there's a slight difference there. But the biggest trend is that durations are getting longer. So we started in 2020, it was around 2 hours. And now that global duration is getting over to around 2.5 hours. That really is a factor of two things. One is the market you're operating in. So if there are markets that are willing to pay for longer duration, for example, California in the US, which is home to some of the biggest battery projects in the world, they tend to be 4 hours because the California market will pay for 4 hours. Whereas other markets, for example, Texas or the UK, tend to be 2 hour markets. It really depends on what that market is asking for. The other thing is that as battery costs have come down, especially cell costs, it's become easier to make longer duration batteries. LFP used to be only competitive in that 2 to 4 hour range. We've started to see LFP being more competitive in 6 hours, 8 hours. But then as we move to really long durations, we move into other technologies, as we'll talk about a little later today. Next slide, please. This is a leaderboard of the individual projects. So we were looking before at countrywide deployments. And as we mentioned, China has really taken over, at least on a gigawatt basis of installations or gigawatt hours. China was over 50% of all installations in 2025. That said, the US is number two, but the US tends to lead in individual projects that are brought online. There's a big race going on right now to see who can be the first to bring on a 1 gigawatt BESS. To my knowledge, and I actually just searched before this presentation to make sure it was true, but no one has brought on a 1 gigawatt project. There are some where they will talk about a project being multiple sites, but when I say project, at least, I mean a single interconnection point on the grid. That has not happened. There are a few under construction right now, but no one has reached that, crossed that threshold. That Edwards and Sanborn is the leader right now in California at 821 megawatts. But there's several contenders that are coming for this title and hoping to bring on that gigawatt scale battery. You can see there's a few in Saudi Arabia, which is a real newcomer to the area. They hadn't had many projects online, and just in the past couple of years, they started bringing on some really big ones. And you can see they have two in the top 10 listed here. One important thing to note, we have a whole separate safety section in the report, but we do mention here that one of the biggest projects in the world, which was a 750 megawatt project in Moss Landing, also in California, did have, unfortunately, a catastrophic fire in 2025. And that meant that a portion is offline, and I believe even still the rest of the entire project is offline, which is unfortunate. I think eventually the other parts of the project will come back on. But it goes to show that while there's a race to build big projects, there's always safety risks that come with those projects. Next slide, please.
Cool.
I think Crystal, no? Okay.
Yeah, I'll take
Thank
it
you.
from here. Yeah, thanks, Drew. So now we're going to start looking about what's changing under the hood. So there's kind of two themes in the BESS market. One is kind of architecture choices at the plant level, like a DC block versus AC block, modularity, as Drew alluded to, and then chemistry choices, especially as the market starts to stretch towards longer durations. So this slide kind of anchors the reality of what chemistries are ever present in the BESS world. And one thing's clear, lithium ion is still the workhorse for mainstream BESS durations because it's bankable, it's manufacturable at scale, has a deep established vendor ecosystem. But what's really changing is where lithium ion's comfort zone ends and where alternatives start looking rational. So lithium ion batteries are still kind of comprising over 90% of the dominant technology, and NMC is kind of fading over the past about 5 to 10 years. Some alternative chemistries like sodium ion, for example, are garnering some increased attention because they've had a few deployments. We have some more slides in the deck, which you can look at lengths on that. If you go to the next slide, Alex, we can talk about what some of the alternative chemistries are. So this is really where different KPIs or metrics really apply here. We're not evaluating everything by energy density. There's a lot of alternative chemistries that are not trying to beat lithium ion at the 2 to 4 hour duration, but they're trying to win where lithium ion is stressed, which is really above 8 hour duration, maybe higher temperature tolerance, lower fire risk, cheaper inactive materials, easier siting and permitting, maybe lower long-term degradation, or kind of a lower dollar per kilowatt hour at cost when it comes to scaling. So some top line metrics that matter a little bit more for alternative chemistries, kind of some of those things that I mentioned, like a cost structure at that longer duration, kind of the O&M model of how serviceable it is in the field. So a lot of different types of chemistry, sodium ion is represented by a number of the companies here. There's flow batteries, vanadium redox being the most common so far commercially. Lead acid, zinc, and metal air batteries as well. And if you go to the next slide. Yeah, based on the chemistry, we kind of predict like a best duration sweet spot. So I really like this framing, and thanks to our partners from Sightline who helped put this graphic together. It's a little bit tiny, but chemistries tend to have a duration sweet spot where their economics and performance are the most competitive. So lithium ion is kind of king at the 2 to 4 hour range, and it's been pushing into the 6 to 8 hour range as costs have dropped over the years. But the 8+ hour world is still relatively tiny to the core market, which is why a lot of what we consider LDES is still early. But I wanted to talk a little bit more about some of the application mapping and give some quick practical examples. So kind of going left to right, and this starts at like 1 hour all the way to 100 hours and multi-day. The 1 to 2 hours are really for fast grid services, ramping some peak shaving. As we move on to the 2 to 4 hour range, this is kind of our bread and butter renewables shifting capacity augmentation. As we move towards the 6 to 10 hours, now you have some deeper solar shifting, evening peak coverage, congestion relief windows. And then as we move towards the 10 to 36 hour range, this is really what we start calling interday, driven variability in case of power outages, system brownouts, winter storms, which a lot of the countries experienced over the past few weeks. And then we get into the multi-day. So this is really resilience, kind of extended wind and solar droughts, kind of more islanded operational support. So although these markets are early stages, this is becoming increasingly important, especially in terms of weather events and supporting the ongoing data center boom, which we have a whole dedicated section of the report on this year. Yeah, if we can go on to the next, I'm going to hand it off to, I think, Alex here.
Drew,
Thanks, Crystal. So this slide here is talking about the two most common architectures for systems. And this is, I think, one of the big trends we've seen in 2025. So just a quick overview of the difference here. As I mentioned before, all utility scale energy storage systems have to have the batteries themselves on the DC side, an inverter or a PCS, as well as some other key components. And then most of those systems are outputting at somewhere around, say, 500 to 1,000 volts from the inverter. And then they want to get stepped right up from the inverter up to medium voltage. So usually you'll have a transformer right next to it. And if we look on that picture on the right, you can see the medium voltage transformers. But there has been a trend toward energy storage product manufacturers, rather than having a separate PCS as a separate component, like is shown on the right, they started building the PCS right into the enclosure for the battery. The first company to do this at a large scale was Tesla. I believe they came out in 2019 with the Megapack product. They're now on the Megapack 3, just got announced in 2025. So for a while, they were the only company that was doing it that way. They were a bit of an outlier. Then Sungrow started doing it a couple of years after, and in 2025 we saw most of the major battery manufacturers start offering AC block products. We're looking at Fluent's product here on the left. That is one of those market leaders. Others who have done it are companies like Wärtsilä has come out with a system, and then many Chinese manufacturers also have gone in that direction. Hyperstrong is one that produces both a DC block and an AC block option on their product. I don't think this is a case where the market is going to go entirely in one direction. Rather, there's been sort of a bifurcation of AC block and DC block products. And I think for a long time, we will anticipate there will be both those markets. It remains to be seen if one is going to win out over the other. If you're going for the lowest cost system, that tends to be a DC block solution. But we've also seen some really big projects get built with AC block, and at a large scale, you can do that quite efficiently. I should note too that AC block tends to be a little more efficient on space because they've packed those components into a single product. So that was one of the big trends that we saw in 2025. This slide is capturing that. We're really excited to see where that continues to go this year. Next slide, please.
We go on? I think this was one of the slides that we wanted to skip.
Sure, yeah. Let's do the next one.
Yeah.
All right. So we have here one important aspect of energy storage systems are whether they're grid forming or grid following. To be clear, almost all the bidirectional inverters, also known as PCS, that are used on these types of systems, the technology in those inverters can do either of these things. They can follow or they can form the grid. However, it really depends on the application that you're going after, whether you want to actually form the grid. Most utility scale projects aren't concerned with forming the grid because they derive their value from providing support to an existing grid. So for example, the big projects I was referencing before in California, like the Edwards and Sanborn 820 megawatt project, if the grid goes out, that system cannot produce any power whatsoever, similar to most residential solar systems. Whereas there are some systems that are able to form the grid, and that could be anything from a residential or a commercial industrial system, where if the grid goes down, you can form a microgrid that's islanded from the main grid, all the way up to the really large utility scale projects can also do that. And some projects are paid to be what's known as black start, which means that if the entire grid were to go out, you could restart the grid by starting that battery, and other power plants will sync up to that battery. That's relatively rare on the really large projects, but there are some markets where that's common. For example, Hawaii in the United States is a market that requires most projects to have that functionality. Next slide, please. So I think this transitions to one of the big points that we saw in the report this year, which is what is driving the growth of energy storage. And I think number one I covered earlier, which was declining cost. You get batteries get cheaper. There's many more cases where they make financial sense to be built. However, it's really important to note that the use case that the battery can go after is dependent on where you are in the market. So we've outlined here 5 of the most common use cases that you see for batteries. There's many more than 5, but these are 5 big categories that cover, I think, most of the large projects that we're seeing. One important distinction to note is some of these are front of meter or FTM, while others are behind the meter, BTM. BTM refers to a battery that is located together with a load, as opposed to front of meter where you don't have a load, you're just connected to the grid, usually through a high voltage or medium voltage connection. So to quickly run through these 5 leading use cases, arbitrage means you're sort of just buying low and selling high, just like in the stock market, that if you have a market that allows you to do that, that can be very lucrative for batteries. Grid support means you're providing various different services to the grid. It really depends on the market, but many markets are willing to pay for certain services that help them maintain the grid. They can pay on a kilowatt or a kilowatt hour basis, whatever, depending on the service. Capacity markets are a great use of batteries. A lot of markets have certain peak hours, sometimes less than 200 hours a year, where they really are constrained. And so if you are a battery that can bid into one of those markets, sometimes that's a pretty large chunk of the revenue that makes sense to go after. Renewables integration was one of the earliest use cases that we saw for batteries. Large batteries were being built first DC coupled, later AC coupled with solar plus storage installations, and that remains to be the case. Even when you have a standalone battery, meaning a project that's built without solar, a lot of times it drives its use from being close by where there is a lot of solar generation back to that arbitrage case where you might have a lot of solar, meaning low prices, then the sun goes down, you're able to discharge and make a very good margin. And lastly, and this dovetails with grid support, but ancillary services is a general term that encompasses a lot of different services you could provide toward the grid. One of the most common there is frequency regulation, which is sort of a fine-tuning mechanism. That was one of the first cases after solar plus storage that energy storage projects really started going after, and it remains one of those key aspects. Black start services that I mentioned before for grid forming, that would also fall under ancillary. Next slide, please.
Yeah, maybe I can take it from here. As we said at the beginning, the sector is booming. Alto, boom and BESS, they don't stay good together. But there are still some bottlenecks that we are experiencing. I think one of the major one is the interconnection time that you have to wait to be connected to the grid, which in some cases, we're talking about multiple years. For instance, in California, the average time in the queue is 9 years, 7 in New York, but also in Europe, we have a huge interconnection queue. Like for instance, in Germany, we have 20 gigawatt of BESS that is waiting to be connected to the grid. And this is a huge bottleneck because, of course, sometimes you have your battery that is ready, you chose your suppliers, you have all the financing that is in the right place, and then you have to wait for the connection grid. So in Europe, at least, there are being developed some prioritization mechanism because right now all the assets that are going to be connected to the grid are considered at the same quality. But of course, I mean, when you introduce a BESS to the grid, the overall grid benefit a lot from this addition to the grid. So they're trying to push a prioritization queue for BESS. But still, it's a huge problem. And it might be one of the reason why we are seeing more and more collocation that is going on. So when we're talking about collocation, we're talking about an asset that has already a grid connection, like it could be a wind farm or a solar or a PV park. And then you add on top of it also the BESS component, which helps you to have a more optimized connection to the grid and also like improve the revenues. Also, other than the grid connection, which is a huge problem, there are also policies that could be good or bad for BESS development. I think around the world, we are seeing many mechanisms on how to facilitate this development. There is the IRA in the US as well. For instance, in Europe, we are seeing more and more the development of capacity market that they guarantee contractual revenues for BESS as well. For instance, in China, we saw there were many incentives to have BESS connected to the grid. As well, other than like these, obviously like economical incentives, there are also other laws that are pushing towards a certain technology of BESS. For instance, this year in the UK, we saw for the first time an auction that was developed just for long duration energy storage, which still was quite dominated by lithium ion, but also other technologies got the spotlight. In China, there are a lot of incentive for long duration energy storage. This year, I think in December, it was connected bigger flow battery in the world, which is 200 megawatts, 1 gigawatt hour vanadium flow battery, which is long duration energy storage, but still 5 hours. But I think also this technology are progressing. And as well, as I said in the chat, in Europe now, especially after the national blackout that we got in Spain last year, there is a huge push to have grid forming capability for batteries because, as Drew said, as far as they are grid following, if the grid goes down, the battery go down with that. But with higher renewable penetration, you need to have more robust grid, and definitely grid forming batteries can provide that instead of the traditional synchronous generator.
Yeah,
I don't know
I
if
could talk to
maybe
this
Chris,
one.
yeah. I'm in Europe, so a bit allergic to US policy.
Yeah, so in the US, the 2025 story is that, storage economics are supported by ITC, but the execution is getting increasingly shaped by tariffs, FIOC or foreign entity of concern style compliance, and supply chain strategy. I do want to take a second because obviously this is a 2025 centered report, and the news was announced in the US yesterday. Some early 2026 news is that the supply chain security lens is getting even more explicit. The US just launched Project Volt, which is a $12 billion strategic critical minerals stockpile backed by public and private financing. And it's really framed at reducing our reliance on Chinese supplies and buffering domestic manufacturers from disruptions. So this really matters for BESS because the emphasized constraints are not just do we have enough critical minerals, but more so do we have price stability, processing capacity, and geopolitical leverage, especially with respect to China. So this slide outlines a lot of the legislation or measures over the past few years and some of the recent policy changes in 2025. So I'll go through them quickly, like the Build Back Better Act kind of set the early direction for manufacturing initiatives and being able to reshore supply chain and shift it towards the US. The investment tax credit or the ITC, accelerated some of the utility scale and C&I developments across the US. IRA policies mostly continued, but was kind of the anchor policy for a lot of our BESS deployments to continue and kind of drove some of the development of factories in the US. Tariffs really raised import costs, especially for companies that were importing cells from China and then doing, pack assembly in the US. Definitely hit by that pretty immediately. And so kind of shift some of our sourcing towards North American supply chains. And then the One Big Beautiful Bill or the OBBA Act kind of disallowed some of the EV or manufacturing credits that had been previously held for the past several years, which also shaped some of our shoring supply. Chinese export controls is also really big news in 2025 because it really increased our supply risk and accelerated this transition towards diversification and building more infrastructure in-house to be more resilient. Not on this slide, but in some of the hidden slides later on, like on the safety side, some of the standards have continued to tighten. So, for example, like the 2026 edition of the NFPA 855 has been pushing more attention towards larger scale fire testing as insurers get more and more prescriptive. So a lot of policy developments in the US front, but as Alex kind of mentioned, across the globe, the overall theme is that storage is increasingly treated as grid infrastructure, not a novelty. So over 25 countries across the globe had implemented or announced energy storage measures, with fiscal or financial or national security incentives as the most common policy type.
Yeah, I want to leave a few minutes for questions from the audience, but just to touch a few points on the data center section. I mean, as I think everybody of you are aware, this sector is increasing a lot year over year, especially driven by the hyperscale. We have seen a huge increase in the US. Other markets are a little bit slightly behind, but they are developing as well. And this could be the measure. I mean, like when you are deploying a BESS, it's either because you want to supply BESS to a grid that has already a huge renewable penetration, or because you have more load. And from the load side, at least in the West, where most of the developing country, I think the data center is going to be the main driver. So more data centers, more BESS that are going to be connected on the grid. We are still seeing that not all the data centers, they choose to have BESS connection from the beginning, mainly because also with BESS, there are delays to get permission and authorization. But most of the hyperscalers indicate the BESS, like the most suitable technology for this kind of application. Also, in the overall in the data center space, not all the battery cover the same role. We have three main different applications. One is the BESS, like battery energy storage, which has an application that is more closer to the traditional application of BESS, so connected to the grid to do energy trade and decrease the overall cost of training and using these neural networks. As well, there is another application, which is UPS. This needs batteries that are able to respond in a shorter term. Thus, they have shorter duration. They're more designed to have high power rather than high energy density. And then there is battery backups unit, which are the one that should be able to provide energy if the whole system goes.